Hello, in this session we shall look at the heat capacity of electrons. Historically, scientists have initially hoped that they can treat the particles of electrons in a metal as if they are particles in an ideal gas. So that means that we are making a very big assumption here. We are assuming that there are only electrons in the metal, and not only do they not interact with each other, but that they don't interact with the atoms that are in the metal. So this may sound crazy, but it is the kind of simplifications that physicists try to make in order to get a sensible and working theory. But as expected, assuming that electrons are simply ideal gases did not work. Let's have a look at the heat capacity for an ideal gas. Now, in an ideal gas, we know that the total energy is 3/2 kBT, which is the average energy of a particle, times m. Number of particles. So to make things simple, I consider 1 mole of the gas, so n is the Avogadro constant. So the heat capacity, therefore, we can get by differentiating with respect to temperature. That gives 3/2 n A kB, and which can also be written as 3/2 R, R being the gas constant. And if we calculate this value, we get a value that is of the order of 10 joules per Kelvin for the heat capacity. And this doesn't even depend on the temperature. Now, what has been measured for metals? For example, there has been a measurement for silver metal at 1 Kelvin temperature, which shows that the heat capacity is of the order of 0.001 joule per Kelvin. So obviously this is a lot smaller. It's a difference of about 10,000 times. So this means that there is something about the physics of electrons in a metal which is very different from a simple ideal gas. So in the last session, I've talked about the Fermi distribution, which is the exact distribution of the electrons. So now we're going to use that distribution to understand why the heat capacity of electrons in a metal is so much smaller than what we would expect of an ideal gas, and to see what is the difference between the two systems. So in order to calculate the heat capacity, we can do that if we know the total energy. Now, and we already have a formula for the Fermi-Dirac distribution, which is the distribution of the electrons at different energies. Unfortunately, it is very difficult to actually calculate the total energy using this distribution. We can, of course, write down an expression for the total energy, like we did for the ideal gas. We can take the Fermi-Dirac distribution, multiply by the density of states, multiply by the energy, And if you integrate that, in principle, we would get the total energy. But this integral is difficult to integrate. So instead of actually doing this integral directly, there's another way we can do it. There's another way we can estimate the total energy and the heat capacity of the electrons. Right. Now we have previously seen that the Fermi Dirac distribution has a graph that looks like that when the temperature is 0 Kelvin. Now for higher temperature, the graph would look like this. Right, that's what it would look like. It would be a smoother curve for slightly higher temperature. And the higher the temperature, the smoother the graph will get. But for temperature that is not too high, the curve will still remain fairly close to the step. So the method that we are going to use to estimate the heat capacity due to the electrons in the metal, for this method we are going to make an assumption. Now we are going to assume that this curve at a non-zero temperature is still quite close to the step. Meaning that if I think about, say, the width of this region, here and here, we're going to assume that the width here is quite small, say compared to the Fermi energy. Now we are going to have to justify this, but let's make the assumption first, derive an expression, and then see if that expression can be justified. So we'll start with this assumption that the temperature is small enough for this shape to be close to the step. So the next thing that we need to do is that we need to understand this part of the distribution. We need to understand how it behaves, and we need to understand a bit more about the curve. Now the reason is that this part of the distribution is in effect the distribution of the excited electrons. If you look at this, when the step becomes a curve, it really means that some of the electrons just below the Fermi energy has been excited above the Fermi energy. That's why the curve just below the Fermi energy becomes lower, whereas the graph just above the Fermi energy, which was 0 at 0 Kelvin, now takes on a non-zero value. Right, so now if we can understand more about this curve, we can make use of this knowledge, hopefully, to then estimate the energies of the excited electrons. And if we know the energy of the excited electron, we will in effect have an expression for the increase in energy with temperature. And that is exactly what we need to calculate heat capacity, the rate that the energy increases with temperature. So let's do that. Now the first thing that we need to do is to obtain an expression for this curve and that curve. And we'll start with the Fermi Dirac distribution. Right. I'll write that down. Fe is equal to 1 over exp that E minus mu over kBt plus 1. I'll continue for the moment to use mu and EF interchangeably. Mu is just EF. Okay. So what I'd like to do now is to obtain an expression for this part of the curve, an approximate expression. The way to do it is this. If you look at this argument here, E minus mu, if we are around this region here, the energy is slightly below, the energy is below mu, the Fermi level. So this means that the argument is negative. Alright? Now, since you are assuming that the temperature is small, then when this expression becomes negative, the exponential will quickly become quite small. So therefore, here Fe will become approximately. Now let me write down the approximation that I'm going to use. I would want to use the binomial expansion for 1 over 1 plus x. So this is approximately equal to, for small x, approximately equal to 1 minus x. Right? Binomial expansion. So in this case, when E is below mu, right, that is negative, and this exponential quickly becomes small. Now if you compare this with this, the x there corresponds to the exponential. I have a plus 1 there and I have a plus 1 there. So this becomes quickly very small, and therefore I can use this approximation to say that this is approximately 1 minus exp E minus mu over kBt. So I have a slightly simpler expression here, just 1 minus this. Now let's see what this means. So this is the approximate expression for this part of the curve, for the part of the curve that is just below the Fermi energy. Now if you look at this curve, there are two terms here, 1 minus the exponential. Now the 1 here is really this horizontal line that we had when the temperature was 0 Kelvin. So this curve here therefore corresponds to an exponential function. So the curve there is approximately an exponential curve that tends towards 1. Now if we have an exponential curve, we can quite easily find the width of the curve. If, for example, I have x there and I have an exponential curve which is e to the power of say minus x over a. If I plot e to the power of minus x over a against x, I will get a curve that looks like this. And the average width of the curve, meaning this distance, the average value of x, would be equal to a. So that's what we know from the properties of an exponential curve. And therefore, if you compare these two, the x there corresponds to the minus x there corresponds to the e minus mu. Therefore, the a there corresponds to kBt. So this immediately tells us that the width of this part of the curve is approximately k, b, t. And now we have an expression for the range of energy from which electrons are excited. In other words, in an interval of energy that is approximately kBt, just below the Fermi energy, it is from this interval of energy, mainly from this interval, kBt, that electrons are being excited above the Fermi energy. Now that's going to be useful. We'll see how to use it afterwards. So let's just remember that. Now the next thing we're going to do is we're going to apply this same idea to understand this curve which is just above the Fermi energy. Right, so let's do it. When we are above the Fermi energy, E minus mu is more than 0. So we have an exponential with an argument that's more than 0, and it would get quickly very big. Alright, so the exponential will quickly get large. It will quickly get a lot larger than 1. So therefore, I can neglect the 1. So I can neglect that, and all I have is 1 over this exponential, which I can therefore write down as e xp of minus of the argument. So this is what I get. So that's even simpler than before. I don't have an extra term of 1 anymore. It's just an exponential with a negative arguments. So this means that this curve there above the Fermi energy is approximately an exponential function. Or we can think of this as giving us the distribution of the electrons above the Fermi energy. Now we have seen distributions that are given by exponential functions before. That was the Boltzmann distribution. And the last time we have seen this Boltzmann distribution was when we looked at the ideal gas. So the ideal gas has a Boltzmann distribution. Now to make it more obvious, let me rewrite it in this form. I can write this as exp of, I can separate this into two exponents. So this will be minus e over k b t, and the mu part will be exp of plus mu over k b t. And separate it into two exponents, and I can rename this as a. And since mu is a constant with respect to energy, so if we do that, it becomes quite obviously the Boltzmann distribution. Now from our knowledge of the ideal gas, that the fact that ideal gas also has a Boltzmann distribution, this tells us something very specific. It tells us that the distribution, that the electrons above the Fermi energy are roughly distributed in the same way as the particles in an ideal gas. So therefore, or in other words, the electrons, the excited electrons, behave approximately like an ideal gas. Now if this is the case, it is very useful because we know the formula, we know how to find the heat capacity and the total energy in an ideal gas. So although we have seen that from the experimental evidence that we cannot treat all the electrons in a metal as an ideal gas, well, at least we see from this result that we can treat the excited part as approximately an ideal gas. So what we are going to do now is we are going to try to find the total energy of the excited electrons and see if that can give us the correct heat capacity. Right, before that, just one more thing to mention here. We, let's see. Right, okay, we don't actually need this, but it would be of sort of interesting to note that the width of this distribution of the excited electrons can be obtained by again comparing this exponential graph with this argument in the distribution. If you compare the two, then clearly the width is again given by kBt. So that this width is also kBt. So in that way, these two parts of the curve is quite symmetrical. Okay, so let's move on. So let's find the total energy of the excited electrons. Let's write down what we need. Now for an ideal gas, the total energy is given by, as we have seen, U is equal to the average energy of the particles. Right, this is the average energy the particles, and multiplied by the total number of particles. I'm going to use letter n to represent the number of particles of the excited electrons. So the letter n just refers to that part, rather than big N, which refers to the whole lot. This is what we want. So that means that the first thing that we need to do is to calculate, find an expression for the number of excited electrons. So to find this number, we make use of the fact, our knowledge that the excited electrons mainly come from this small interval of kBt just below the Fermi energy. Now we can estimate this number quite easily. If you start from, if you think about 0 Kelvin, at 0 Kelvin, all the electrons below the Fermi level are occupied. Right? And as the temperature is raised, the electrons in that interval of kBt gets excited. So how many electrons are there in that interval? Well, the number of electrons there are as many electrons in this interval as there are states, because at 0 Kelvin all the states are occupied. So to find the number of electrons, all we need is to count the number of states in this interval kBt. Now we know how to count the number of states. All we need is to take the density of states and multiply it by the energy interval. So the number of excited electrons will be the density of states times the energy interval. Now, and as before, it's convenient to continue using the formula for the density of states of the ideal gas. So I will assume that the G here refers to the ideal gas density of states, in which case, to count the number of electron states, because electron can be spin up and spin down, so I would, and since the ideal gas formula only gives us the number of energy states, there would be 2 spin states to each energy state. So I need to times 2. Right. Now, we now need to fill in some variables. The E there, we are talking about a small interval just next to the Fermi energy. So the energy of that interval is still approximately EF. So that should be EF. Okay, and the energy interval is kBt, as we now know. So having found this, in principle, all we need is to then substitute this into here for the total energy, and then we can find the total energy, and from that we can differentiate to get the heat capacity. So from this point on, it is quite fairly obvious what to do. Now, so what I'm going to do next is I'm just going to write down an expression, obtain an expression for the density of states at the Fermi energy, just to make the final expression for total energy and or heat capacity look simpler. So to write down an expression for the density of states, the way that I like to do it is to start by considering the total number of states below a certain energy. Now, this total number of states below a certain energy, now if you recall, it is related to e to the power of 3 over 2 with some constants before that, which contains things like volume, mass, and so on. So we don't have to worry about those constants, so let me just call those constants, let me just give a name, say V. Okay, I'll just call them V. Right, if I now differentiate this with respect to E, we'll get the density of states. Okay, and if I differentiate that, this becomes 3 over 2b e to the half. Right, which is what we expect. Density of states is related to square root of energy. So then, I will divide this. Let me divide the second equation by the first equation. The b and the b cancels, it's 3 over 2, and e to the half divided by e to the 3 halves gives just e. Alright, I have this expression here. So therefore, Ge is equal to 3 big G of E over 2E. Now at this stage, we can make use of the property of Fermi energy. Now, if I substitute Fermi energy into E, we find that we have this expression. Now let's think about this big G of EF. So big G of EF is the total number of states below the Fermi energy. Now we know that all the states are occupied, alright? So, and since each state of this big G refers to the energy states of an ideal gas, if we multiply this big G by 2, we should get the number of electrons. So let me just multiply the top and the bottom by 2 here to express that in terms of the number of electrons. So 2 times big G of EF should be n. So now I have an expression for little n. Okay, it would be 2 times GEF, which is that. So GEF would be just this. Okay, where this part there is actually n. So let me write this out. I have the 2 there, I have 3 times n. In the bottom I have 4. The E dash should be EF. Then I have a KBT. So times that. So now I have a fairly not too complicated expression for the little n here. Now we can put the whole lot together. So U then is equal to 3 over 2, and we have n given by this, which is 3n over 2 and 4 gives 2 at the bottom, EF, times KBT here and the KBT there. So KB squared, T squared. Now we have this expression. And if let me simplify that, that gives 9 over 4 n over EF KB squared T squared. And from this we can finally obtain the heat capacity by differentiating with respect to temperature. And that gives, T squared becomes 2T. So 9 over 2 n over EF KB squared T. There, we have this expression. And this time, if you actually substitute, calculate the Fermi energy for a metal like silver metal that I've mentioned last time, and say if you do it for 1 mole of particles, so N would be the Avogadro constant, and at 1 Kelvin, you will actually obtain an expression a number for the heat capacity which is much closer to the measured value than what you get if you use the ideal gas formula. So therefore, what we have learned here is that it is wrong to think of all of the electrons, we are referring to conduction electrons here, to think that all of the conduction electrons in a metal, it is wrong to think of them as behaving like an ideal gas. But, and the reason for that is because they are all stacked up in the energy levels, so that most of them cannot be excited, because that if an electron tries to get excited, the states above it are all filled up and they can't go up because of the exclusion principle. However, those near the top, within KBT of the highest level, those can get excited, and those that do get excited do behave like an ideal gas. And as long as we find the correct number of excited electrons, we can treat those as the ideal gas, use the ideal gas formula for total energy, and finally find the correct expression for the heat capacity. So that's how it works. Now, one last thing. We need to, just to finish up, we really need to justify the assumption that I started off with, which was, if you remember, I've initially assumed that this interval here is a lot smaller than the Fermi energy. Now, how do we justify that? Well, we know the formula for Fermi energy. So as I've said, it depends on things like volume, mass of the electrons, number of electrons. So these are, we can think of an example like say of any metal, like say sodium or silver metal, say sodium metal, and we can put in the numbers for the mass, number of particles and so on, say for 1 mole of sodium, and we can find a value for the Fermi energy. Okay, we can actually do the calculation, and if you then calculate the width, which is KBT, which we derived along the way, say at a temperature of 300 Kelvin, somewhere close to the room temperature, and you compare this number with the Fermi energy, you'll find that the KBT, the width here, is about 100 times smaller than the Fermi energy. Alright, so once you've carried out this calculation and checked the numbers, we can finally convince ourselves that this interval is indeed very small compared to the Fermi level, at least for typical metals at room temperature. Right, we'll stop here.